Okay, so this is a continuation of chapter 2 about water, acids, bases, and buffers. The rest of this chapter will be discussing about acids and bases. But first, let's talk about ionization of water or self-dissociation of water molecule. Most properties of this solvent, water molecule or water solvent, can be explained using the neutral uncharged molecule. But sometimes we need to take into account the ionization of water molecule. Water molecule undergoes ionization and forms a hydrogen ion and OH and hydroxide ion. So the ionization of water is very small, and so very small molecules undergo ionization. Usually we write water ionization of water like hydrogen ion and hydroxide ion, but in reality a hydrogen ion or the proton does not exist in solution, but it exists as a hydronium ion, hydronium ion, and this forms because when a proton forms, immediately it connects to water molecule. So if you have here the water molecule, now the proton comes here, so you have here hydrogen and the oxygen becomes plus. So this is hydronium ion. So the reaction is reversible and it can go in both ways. So we use equilibrium constant. The position of equilibrium can be obtained using equilibrium constant. This is equilibrium constant. So this value will tell us the position of the equilibrium. So we are trying to quantify the ionization of water or dissociation of water molecule. So to quantify, we have to find the position of equilibrium. So this value K equilibrium will tell us where the equilibrium is. So it's this reaction quotient, the concentration of the products divided by the concentration of the reactants. So equilibrium constant can be calculated or can be obtained from measurement of electrical conductivity, So from the electrical conductivity we can calculate a K equilibrium, because if you have a cell where you have the anode and the cathode, the hydrogen ions will go to the cathode and hydroxide ions will go to the anode. So in that way we can measure the electrical conductivity and find out the equilibrium constant. So pure water, very pure water at 25 degree, the equilibrium constant is 1.8 times 10 to the power minus 16. Here we can multiply the concentration of water and equilibrium constant, and then we get the ion product of water. This is called the ion product of water. So how do we calculate this value, the ion product of water? We can easily calculate by multiplying this value we get by electrical conductivity and multiply to the concentration of water. So the concentration of water is 55.5 molar. How do we get this number? Pure water at 25 degree, the concentration is grams in 1 liter. Grams in 1 liter is what? Is 1000 grams in 1 liter. Okay, so if we divide this by the molecular weight, which is 18 gram per mole. The molecular weight of water is what? 18 gram per mole. So if you divide 1000 to 18 gram, we get 55 mole per liter, which is the concentration of water at 25 degree, very pure water. So if you multiply this with 55.5 and this number, we will get the ion product of water. So this is the equilibrium constant and this is the concentration of water. So the value of the ion product of water, so if you multiply the hydrogen ion concentration and the hydroxide ion concentration in an aqueous solution, you get this value: 1 times 10 to the power 10 to the power of minus 14, 1 times 10 to the power of minus 14 m square, which is the Kw. So Kw is the ion product of water. So if you have the same concentration of hydrogen ion and hydroxide ion concentration in the solution, then we have neutral. So the pH, we say we have neutral pH. So this is what? Neutral pH. Because the concentration of hydrogen and hydrogen is equal. So we can easily calculate the concentration of hydrogen and hydroxide ion from here. Okay, because we have Kw equals concentration of hydrogen ion equals concentration of hydroxide ion. So it's going to be concentration of hydrogen ion square, because the concentration of both are equal. So hydrogen ion concentration is going to be what? It's going to be the square root of Kw. Square root of Kw. On hydroxide ion concentration, so this is concentration, this is square bracket, and here OH ion. Concentration of OH ion is also the same, which is square root of Kw. So we can calculate the concentration, because when you multiply these two, you get 1 times 10 to the power of 14, and when you square root of this one will give you 10 to the power of -7. So the ion product of water, is now forms the base of the pH scale. The pH scale we know, which has the value from 0 to 14, comes as a result of ion product of water. It was devised by a guy called with the name Sorenson in 1902. So it ranges, hydrogen ion can range from 1 molar to 1 times 10 to the power of -14. So if you have 1 molar of hydrogen ion concentration, the pH will be zero. Why? Because the pH is just another way of showing the concentration of hydrogen ion. Okay, so if the concentration of pH equals to 0, here pH equals to 0. Okay, if the pH is if the concentration is 1 times 10 to the power of -14, then your pH is going to be 14. Your pH is going to be 14. Okay, so minus log, the word pH is negative logarithm of hydrogen ion concentration. Okay, so this P stands for the negative logarithm. Okay, it stands for the negative logarithm. The negative logarithm. It's not the power, it's not the potential. So many students will tell you P stands for the power of hydrogen. No. The correct thing is the negative logarithm. Okay. So if you have a pH, if you have a concentration of 1 times, if you have a concentration of 1 times 10 to the power of -7, if you have this concentration in your aqueous solution, then the pH is going to be neutral. pH is going to be 7, which is the neutral pH. Okay, we'll stop here, and then we will start discussing about the weak series and weak bases.